talk about some problems on geometrically exact beams. It's based on the following publications. First, the A1, A2, A3 are journal papers which have been accepted. Apart from that, with Mark and our supervisors, we wrote a conference paper for the CDC 21.
Charlotte, please get closer to the microphone because they hear you. Sorry.
Okay.
Thank you.
What I'm presenting today is based on the 3 first papers. And apart from that, with Mark and our supervisors, we wrote a conference paper for the CDC 21, which has been accepted. And I will briefly mention a last paper, which is in preparation. So why do we call them a geometrically exact beam? It's because the model, even though it's representing beams where the strains are small, the strains are the local deformation in the beam, the motions of the beam are big, are large. By that, I mean large displacements of the reference line, which is the red dashed line, whose position is given by the P, the red P, and the large rotations of the cross-sections, which are the blue circle on the picture. And if you have the position of the center line and this rotation matrix R in blue, which gives the orientation of the cross-section, you can recover the position of the beam as the P bar here on the picture. And because the model accounts for large motions, it has a nonlinear governing system. This is why sometimes people will also call it the nonlinear Timoshenko beam, or also geometrically nonlinear beam. And I will consider 2 frameworks for this to represent these beams. The first one is when we take as unknown these P and R, the position of the center line, and this rotation matrix whose columns, the BJ here, form a basis which gives the orientation of the cross-section. If we take this unknown, so this P and R, they are expressed in some fixed basis, J here, which can be the standard basis in R3. And if you take these 2 unknowns, then you obtain a system of this form, where V and Z are defined in blue here. So you see that they depend on the P and R. You can see that the system is of second order in space and in time, and it is quasi-linear. And the notation hat here is just a way to represent the cross product. If you take a vector U in R3, the U hat applied to some vector zeta is just the cross product between U and zeta. And in the definition of V and Z, this notation vec is just a way when you have the U hat to get back the vector U. So vec of U hat is just U. And in the governing system, you also see appearing this matrix M, and in the definition of Z, the matrix C. These are just given data. They are called the mass and flexibility or compliance matrix, and they just depend on the material and the geometry of the beam. Also, in the definition of Z, you see the epsilon C, which just gives the form of the beam before anything happens, so before the formation. The second framework is when you take as unknowns Y, which is made of V and Z. So actually, the V and Z that I show you here, they have a meaning. So V contains the linear velocities and angular velocities, both having values in R3. And Z contains the internal forces and moments. So Y now has values in R12. And also each component so each of these vectors in R3, instead of being expressed in the fixed basis, they are expressed in this basis made of the columns of R, which are attached to the beam, which moves through time. And when you take this unknown, then you get rather a system of this form, which you can see is of first order in time and first order in space. Again, you have this notation hat for the cross product. So these are just matrices of size 3. And if you multiply everything by the inverse of the matrix on the left, then you can get a system of written in a more compact way of this form below. Now the system, instead of being quasi-linear, is just semi-linear, and I put the non-linearity on the right-hand side. It's a quadratic non-linearity. And so you have these two frameworks. The first one we just call JEP, more wave-like framework, second order in space and time. And the second one, since it doesn't involve positions or rotations, but more intrinsic variables, I call it intrinsic GEP, so intrinsic geometrically exact beam model. And this one can be seen to belong more to the Hamiltonian framework. And these two systems, if you look at the definition of B and Z I just gave you before, so by definition of these variables, you can see them as being linked by a transformation, which is given here, a nonlinear transformation, capital T. I just want to show you the transformation now because I will go back to that later and see how we can use it. And so this was just the system, the running system for one beam. If you look at networks, for example, a network of beams indexed by I, then the unknowns are also indexed by I, as here. Just recall that Y is made of this V and Z, the first last six components. The difference when you consider a network is that you have to specify what is happening at the junctions. So several beams are meeting. Here we assume that at the junction, the beam will remain attached to each other, but also that they don't change the angle between them. So we call that a rigid joint. And also, so this is a classical condition. We assume that a Kirchhoff condition, that the forces, internal forces and movement, which are exerted by the beam incident to the node, are balanced with the external load at this node. So this is in terms of positions and rotations, but you can also translate that in terms of the velocities and internal forces and moments for the IJET model. Then you get these two conditions, the continuity of velocities and a Kirchhoff condition where R here is just like epsilon C before it just corresponds to the form of the beam before the formation. And for simple nodes, so where there's just one beam attached, then we either set the internal forces and moments or the velocities to be equal to some function. I don't want to go into details on the well-posenness, but you can show that there exist local in-time solutions for the system. So for short time intervals, you can also show that there exist semi-global solutions. So that means that you can choose any time interval where you want a solution, you will have one, but if the initial and boundary data are small enough, that the smallness will depend on this time interval. But to get this well-posenness result, we in particular need to have some regularity of the eigenvectors and eigenvalues of A. And in particular, if the mass matrix and the flexibility matrix are dependent on X, we have to add some assumptions to get this. So this is why I wrote the assumption 1 here, but you don't need to remember it. It's just that you will see it appear in the theorem later because we always use it in order to get the well-posenness. So now I want to talk a bit more about this transformation, what we can do with it. So I record it here. So the relationship between the P and R, the unknowns of the JEP model, and Y made of V and Z, the unknown of the IJEP model. And I will take as an example just the case of a single beam, but we could also work with networks with a few more arguments. So here we take one beam, which is clamped at x equals 0. And at x equals L, we apply some feedback control, but we could take a beam which is free at x equals L. It does not matter here. And you have the Jeb representation of this beam and the iJeb counterpart. You can see where the beam is clamped, the velocity are 0. And in fact, the transformation between the two models, we can invert on some specific spaces in E1 and E2 here, where you see that E1, the definition of E1 involves in red the Dirichlet boundary conditions of Jeb and the initial condition of order 0, while E2 involves these three conditions, 3A, 3B, and 3C, where 3A is related to the last 6 initial conditions of the second system, iJeb. The green conditions are related to the last 6 governing equations of system 2. And the blue conditions, 3C, are related to the boundary condition at x equals 0. So here U is just almost the same as Y. It's multiplied by this block diagonal matrix. In fact, U is made of the velocities for the first 6 components and the strings rather than the internal forces and moments for the last 6 components. And what we want to show with these two spaces is that the transformation T is in fact bijective in these spaces. If we take also some compatibility condition between the initial and boundary data. Why is it interesting to have this lemma? It's because then we can prove this theorem, which says that if the data has some regularity, and if you take the initial data for the iJeb system such that you keep the link with that of the Jeb system, then you can prove that the existence of a unique classical solution to system 2, to the iJeb system, implies that of a unique solution to the Jeb system. How to do that? You can see that any function, any solution to the system 2 is in fact always in the set E2. And then you can use this lemma, which will give you automatically a candidate PR, which would be a solution to the second order system, the first system. And we can use the remaining governing equations of the iJeb system and the remaining initial conditions and boundary conditions to get those of the first system. So now how to prove this lemma, that the transformation T is bijective. So we want to show that if we have any element in E2, we can find a unique PR in E1 such that T of PR is equal to Y. But T of PR is equal to Y is this equality here in blue and red. And if you move things a bit, you can also write it as a system of linear PDEs, these two systems for P and R which are coupled. And what we did is that we didn't want a system where the unknown, so here the system on the left where the unknown is the rotation matrix. So we parameterize the rotation matrix with the quaternion. So quaternion is a vector in R4, which is related to the rotation, which represents the rotation matrix and is related to it by this equality identity here. And in fact, one can see that this system for R is equivalent to this system for Q. So now we have a system where the unknown has values in R4, but still the two systems for P and for R, it looks like there are too many equations compared to the number of unknowns. Because here we have 6 equations, but only 3 unknowns, and here 8 equations, but only 4 unknowns. So, but we have not used yet the the green conditions, which appears in the definition of P2. And these green conditions, in fact, gives compatibility condition, which will help to solve these systems. So the last three green conditions will give this identity here, which can be used together with the lemma given here to prove that there is a quaternion solution to the first system. Once you have this, you can get the rotation matrix and inject that in the second system for P. And again, it looks like it's overdetermined, but you can use the first three green equations to show that in fact there exists a unique solution. So this is for the transformation. And then thanks to this transformation, you can then always, if you have a problem that you want to set for the system in terms of position and rotations, if you manage to translate this problem so that you can solve it for the JEP system, which has a nicer, for which there are nice mathematical results, then you can also get a result for the original system. Now I want to talk about a different problem. So this is the problem of exact controllability of nodal profiles. I will consider the iJEP system, but again, we can also translate some results for the JEP system afterwards. The problem of controllability of nodal profile is that at some nodes, which are the squares here, you want the state to meet some profiles on some specific time interval. And to do this, you control some other nodes, which are the triangles on this picture. This time interval on which you can control the system will depend in particular on the traveling time of each beam. What do I mean by that? I said before, or maybe I didn't mention it, but for the iJEP system, the matrix A is hyperbolic. And in particular, it implies that the eigenvalues are real. Here, there are some negative and some positive eigenvalues, which are the lambda k. And in terms of these eigenvalues, you can define what is called the traveling time, which is the time needed for the information to go from one boundary of the beam to the other. Now I will concentrate on this A-shaped network on the left. For such a network, you can prove that you can reach any given nodal profiles at the tip of the A if you control at the simple nodes 4 and 5 here the internal forces and moments. And the time interval on which you can control, which will be T star capital T, depends on these traveling times on each beams as follows. So T star has to be large enough. And to do this, we use the constructive method, which has been introduced by Tatien Lee and his collaborators, and in particular his work with Zhuang in 18 and 21. Why is it called the constructive method? It's because we will build a solution for this system, edge by edge, in such a way that it satisfies the boundary condition, the transmission conditions, the initial conditions, and also these nodal profiles. And then once it's built, we can take the trace at the control node to get the desired control. So on the drawings here, you have this A-shaped network, and in the vertical axis is the time. So what you want is the solution to fulfill these profiles in red over the time interval T star T. And to solve, we will not always be solving forward in time. I mean, we will not always solve the system like this, but we will also solve sidewise, which means that the role of the T and X are switched. So in some way, we are considering this system on the right. So the procedure is as follows. First, you need to solve for the whole network at once, the system, until the time T star, which is defined here. once this is done, you get the trace of the solution at the node 1 where you want to profile. So you get this orange trace, and in between the orange trace and the profiles, you can link these two data so that you get some initial data for the next step. And the next step is to solve sidewise, so from boundary to boundary, as in the step 2 here, so that you get solution for the 2 incident edges. And once we have done that, you have some data that you can use to solve this time forward in time, as in step 3. And then you get, thanks to this, again, data at the multiple node to solve sidewise in time for the last 2 edges, as in step 4. And you can get the controls that you wanted. But why did we need the control time to be larger than this quantity in red? It's because even if we have constructed the blue solution in step 2 to 4 in such a way that it fulfills all the transmission conditions of the network, we need to prove that it also fulfills the initial conditions. And to prove this, we need to show that this blue solution in fact coincides with the orange solution on some domain which includes where the initial conditions are fulfilled, which is the green domain here. And this green domain is defined notably in terms of this traveling time from one side of the edge to the other. So this is a sketch of the method. And the final word is for working preparations, where instead of taking a rigid joint, as I mentioned before, we want to represent a joint where so here it's first for strings, where the strings are coupled at the multiple node to an elastic body. And to represent that, the multiple node is expanded into a network itself, which is made of springs and masses. And we consider for this kind of network, here you have a star-shaped network, a controllability problem where you control all the simple nodes except one which has some delicate boundary conditions. And so for future work, it would be interesting to see how to model this kind of junctions and see this kind of controllability problem for geometrically clips instead of strings. I didn't talk at all this time about the stabilization, but there are many questions which appear during the work, and it would be now I'm trying to see what is the effect of applying feedback control numerically at one boundary of the beam, and it would be very interesting to see also what would be the effect of structural damping in the equations on the stabilization and well-posenness results if we can relax the smallness assumptions on the initial data which appeared on the proof, and also on stabilization. It would be very interesting to see for a star-shaped network if it can be stabilized, even if we remove one of the control, if we remove the control of one of the simple nodes. And finally, on the nodal profile controls problem, which I last mentioned. So in the literature, there appear some conditions which seem to be sufficient to condition on the network, on the position of the control nodes, the number of control nodes, and this kind of things which seem to guarantee exact controllability of nodal profiles. But it would be nice to have a theorem which would say if these conditions are satisfied, then we can get nodal profile control for any network which will satisfy this condition instead of working case by case. So that's all. Thank you for your attention.